Would you like to go ahead and put on the lapel microphone? You can say a few words, make sure it's picking me up.
Okay, check 1, 2.
So it might be better closer to just once it's green.
2. Check 1, 2.
So it's not picking up. Are you all set with
Everything's good.
okay, good.
Okay, well, good afternoon and welcome everybody to the Ford Lecture. I'm David Gertis. I'm the chair of the physics department. It's really my true pleasure to welcome all of you here today. The Ford Lecture has traditionally been an annual or nearly annual event in our department, but this is the first lecture we're having since February of 2019, I believe. A few things have happened since then to put off subsequent Ford lectures, and so I'm delighted that we have finally the ability to return to these in-person lectures that are such an important part of our life as a department and a community. This lecture series has been made possible by a generous endowment from Ford Motor Company. And do we have any, I think Mike Taymor is here from Ford. Welcome, Mike. Thank you. Do we have any other current or former employees of Ford Motor Company in the audience here today? How about anyone who drives a Ford? All right, so thank you again. Just a couple of items of housekeeping, so to speak. There will be Q&A after the talk. And when you ask your question, we ask that you wait just a second so that one of our runners with a microphone can find you and your question can be heard. And now to introduce our speaker, I'd like to welcome Eric Spanton to come up front. Eric is our newest faculty member in the Department of Physics, or at least our newest until this morning when we just got acceptance of a new faculty member for the fall. Eric joined our department in fall of 2020 as a LSA Collegiate Fellow and then moved on to the tenure track this past fall. Their research is inspired by and builds upon some of the work that you'll hear about today. So Eric, take it away.
Everyone hear me okay? Great. Yeah, thanks, David, for the opportunity to introduce our amazing speaker today. So you can read about in the pamphlet of his academic history, but what I wanted to do is give you a sense for how exciting this work was to me as a postdoc at the time and to almost everyone in our subfield of condensed matter physics. So the largest meeting for our subfield is the APS March meeting, where over 10,000 condensed matter physicists congregate to a city every March. And in 2018, that was held in Los Angeles. Leading up to the meeting, I know in the group that I was working in, there were whispers and rumors that Professor Jarillo-Herrero had found superconductivity in the system. That no one had, it had been predicted, but no one was, actively working on it in our group. Those whispers turned into conversations at the March meeting. It was socially the easiest March meeting for me because every person I talked to asked my opinion about it because I was also working on graphene at the time. And as his Wednesday talk came up, the March meeting announced that they would have overflow seating and project his talk in a large room on a large screen. And I was sitting there as the talk was starting to happen. We sort of hung out 30 minutes before. People started to trickle in. At some point, we were like, wow, there are no more seats in here. And everyone was sort of standing around the screen. And this was not even the room where he was giving his talk. And then we saw people on the second floor on the balconies looking over so they could get a better view of the screen. And so it's rare that you can get physics to agree that something is interesting. And I think almost everyone at that March meeting was incredibly excited to hear his talk. It definitely delivered, and I'd say in the following years, the promise of that work has been borne out in dozens of research groups whose paths have been altered by this amazing work. So with that, I'd like to introduce Professor Jarillo-Herrero from MIT.
Thank you very much, Eric and David, and everyone for the warm welcome today to Michigan. And I want to thank also Ford for sponsoring this lecture. And it's one of the first in-person talks that I gave after after 2020, and as my travel schedule started to resume, my wife told me, it's okay, you can travel, but you have to wear a mask because my mother is here and I don't want you to bring back, strange things with you. So I will keep my mask on. You can feel free to do whatever you want. It's just, I know this is being recorded, so my wife will have proof that I wore my mask, when I get back home. So thank you very much, Eric. Indeed, I'm going to tell you about the magic of Moire quantum matter, and this is something which is a relatively new, a few-year-old field, okay, and something that is I find fascinating and that I'm very happy to share with you. Now, before I speak about Moire quantum matter itself, because I know that this is a broad audience, let me first comment on the fact that among the most fascinating states of matter that we have in the universe are those where the interactions between the constituents of that matter are very strong. And this is something that happens in all areas of physics. Okay? For example, you have this in a state of matter called the quark-gluon plasma. This happens a few hundreds of nanoseconds, microseconds after the Big Bang. Okay? And it's something that we can recreate nowadays in collisions between heavy ions at accelerators such as Brookhaven National Laboratory. You also have these strongly interacting phases of matter in the different phases of nuclear matter in neutron stars. I think I think the camera. So I'll stay here. I'll just bend. So Here's a picture from the Chandra X-ray Observatory of a neutron star. And if you go to Wikipedia, you can see that there are different phases in neutron star. They call them nuclear pasta, so it's actually very interesting. They have the lasagna phase, the bucatini phase, the spaghetti phase, As usual, the astrophysicists are much cleverer than everyone else about naming objects, and we just try to tag along. And then, perhaps a bit closer to my heart, to my field, are the different topological phases of, for example, two-dimensional electron gases. When you subject them to a strong magnetic field, you can have, all kinds of very exotic phenomena, such as, fractionalized charges and various, topological phases of matter. So, all of these, in all of these systems, the interaction between the constituents that make that matter are very strong. If you zoom into strongly correlated quantum materials, and with electrons now are the key, protagonists, then this describes, this includes many vast families of materials, and perhaps the most studied to date is the family of high-temperature cuprate superconductors, where in a phase diagram of temperature here versus doping or versus charge density, we have a variety of phases, few of which we have a good understanding of, even to this day, despite almost 4 decades of theoretical work on this subject and experimental work on the subject. So, in general, the difficulty with these systems, and more generally the difficulty with strongly interactive systems, is that these systems are very hard to solve theoretically. Okay? So, for example, take this copper oxide, these high-temperature cuprate superconductors. The key action happens in these copper-oxygen planes, okay? Where in the compounds that you grow stoichiometrically, you have 1 electron per copper atom, okay? And these electrons interact very strongly with each other. They repel each other very strongly. And as a result, they are stuck in their positions, and they cannot conduct electricity. They form a state of matter known as a Mott insulator. It's a special type of correlated insulator, so Mott insulator. And now a funny thing happens when you remove a few of these electrons. Okay? Now there are some empty sites. So some electrons can jump onto neighboring empty sites. But they have to do this in a sort of correlated fashion. And this correlated fashion sort of magically produces superconductivity. Okay? And we do not understand how that happens. The simplest model that people believe captures the essential physics that I described is this thing called the Hubbard model, where you have some energy penalty to put 2 electrons in one site because they repel each other. And you also have hopping between occupied and empty sites. And even this very simple model, we cannot solve it analytically, okay? Despite more than 30 years of research, for more than a few particles. Yeah? So we do not know how to go from this model to this type of diagram, even though we believe this has the essential physics responsible for everything that is happening here. Yeah? Now, the difficulty in trying to theoretically solve the problem of strongly interacting electrons has led to alternative platforms to see if we can simulate these problems and gain more insight than what theory can provide at the moment. And one of the most successful platforms is that of using ultra-cold atoms in optical lattices to simulate strongly interacting matter. Yeah? So back already now 20 years ago, okay, the group of Immanuel Bloch, Marcus Greiner and the group of Immanuel Bloch, they were able, they would shine lasers against each other. They would create this periodic potential where they could load atoms, and they have a tuning knob with which they can change the strength of the interaction between the atoms. And they could, for example, realize a transition between a Mott insulator and a superfluid. Okay? They did this with bosonic atoms, so atoms with integer spin. Yeah? A few years later, they were able to realize similar physics with fermionic atoms with half-integer spin. And just to give you an idea of what is the latest in this field, so as of a few years ago, they were able to realize antiferromagnetism in the Fermi-Hubbard model. Okay, so they could put these atoms in a lattice, and they could see that they're mostly spin up, down, anti-correlated. Okay, so antiferromagnetism. So these, in the cold atoms community, we're beginning to explore this corner of this phase diagram. They would like to explore the entire thing, and in particular this region, where they would like to see D-wave superfluidity originating from repulsive interactions. But in order to do so, they have to go down in temperature 1 or 2 orders of magnitude lower than they currently are. And they're already working at about 100 picokelvin, okay? Now, there is no fundamental physics obstacle to doing so, but it's extremely challenging technically, and for many years they have been trying and they haven't yet been able to get to such low temperatures. Huh? So we have these two, let's say, traditional platforms to investigate strongly correlated quantum matter and topological physics. We have quantum materials, the real materials that we go, crystals, which have lattice constants, typical length scales of the order of an angstrom or a few angstroms. And we have, since the past 2 decades, cold atoms in optical lattices with the typical length scale. The distance between the atoms here is about a micron. And what I want to tell you about today is about the discovery of a new platform. We call it Moire quantum matter, where the typical length scale, the Moire length, is of order 10 nanometers. So it's conveniently 2 orders of magnitude from either of these other 2 platforms. So it fits in a very complementary space to investigate this type of physics. Associated with these length scales are temperature or energy scales, okay? So in quantum materials, we have typical temperature scales of the order of 100 to 1,000 Kelvin. In cold atoms, 0.1 to 1 nanokelvin. This one, because we have intermediate length scale, we also have intermediate temperature scale, something about the 1 to 10 Kelvin, 1 to 100 Kelvin. Okay? And that's a very convenient temperature scale to investigate in a solid-state physics laboratory. So initially, the development that enabled this Moire quantum matter platform was the fact that we have been able to do now something that we couldn't do in the history of material science, and that is the fact that we can put 2 crystalline lattices on top of each other with any angle, with any relative angle between the 2 crystalline lattices that we want. Okay? That's something that you cannot do when you grow crystals thermodynamically. You cannot do that when you grow crystals by molecular beam epitaxy methods. This is something that we were only able to do with the advent of 2D materials. Once we have 2D materials, 1 atom thick materials, we can get one and stack it on top of another one with any angle that we want. Okay? This can be 10 degrees, 5 degrees, 1.1 degree, as I will show in a moment. Let me stop this before you get dizzy. So this is something that we weren't able to do before, but as I will show you, it can modify dramatically the electronic, optical, and mechanical properties. I will focus on the electronic properties of materials. Okay? Now, why would you want to investigate this Moire quantum matter? Okay, so I'll be telling you about this in the rest of the talk, but let me just give you a few reasons. So, to me, one of the nicest things is that you can easily obtain, when you create this Moire quantum matter, isolated flat electronic bands. And that means that with this, you can investigate the interplay between the kinetic energy of the electrons, energy momentum, the band structure, and the interactions, the Coulomb interaction between the electrons, and also the topology, the topological properties of those electronic structures. Okay? Now, and there are very few systems where you can do all of these. With a few simple building blocks, for example, I will show with graphene, hexagonal boron nitride, or transition metal dichalcogenides, simple semiconductors, you can find enormous amounts of correlated states of matter and topological states of matter, okay? Which brings up the question of what are the key ingredients which are essential in order to obtain emergent quantum behaviors of matter. To some extent, you can get rid of the chemistry. You don't need to have complicated compounds, heavy fermions, uranium compounds. You can do it all with carbon and a few other things. This is a very highly tunable in situ platform. You can control things by applying electric fields, electrostatic doping, strain, pressure, magnetic field, temperature, etc., and tunable through the twist angle and Moire system. So it has an element of those ultra cold atoms lattices that you can control and tune things, quite precisely. Okay? Much more than we were able to do in traditional condensed matter systems. And finally, this novel experimental platform allows you to explore vast new families of hybrid materials based on non-equilibrium growth and assembly. The type of materials that we're investigating, you could never grow them in an oven. Okay? So we can reach many more types of crystalline structures and phases that are available otherwise. So with these systems, we have pretty much found in these systems all of the phases of condensed matter systems, was condensed matter physics, like from correlated insulators to superconductivity, various topological phases, magnetism, pneumaticity, Moire ferroelectricity, strange metal, many things, the list continues, okay? So we're sort of, doing almost all of condensed matter physics with a very simple platform and structure. So with this introduction, this is what I want to tell you about today. I'll start by reminding you what graphene is, and then I'll tell you about magic angle graphene. Then I'll comment on the rise of Moire quantum matter, basically what has happened since our discovery a few years ago. And then I'll tell you about an example of sort of this Moire magic beyond graphene. In particular, I'll describe Moire ferroelectricity in bilayer boron nitride. And then I'll tell you about some of the things, I'll just briefly mention things that are going on in the neighboring communities in this field. So let me get started with graphene. So graphene is a honeycomb of carbon atoms, okay? All of these atoms are chemically equivalent. They are carbon, okay? But from the crystallographic point of view, there are two types of atoms. We call them the A and B atoms, or the red and green ball here. And that's because in order to tile a honeycomb in 2 dimensions, you need a 2-atom basis and 2 unit vectors. Now, you can calculate the electronic structure of electrons in graphene, and it's here in a simple quantum mechanical model. And if you zoom in near the Fermi energy, you find this very unusual linear energy momentum dispersion. Yeah? This is something which is very unlike what happens in most materials, where the relationship between kinetic energy and momentum is quadratic, is parabolic. Here you have linear energy momentum dispersion. This is a dispersion which looks more like that of photons or massless ultra-relativistic particles. In fact, the equation that governs this behavior is nothing else but the Dirac equation in 2 dimensions for massless particles, okay? Where you see energy is linear in momentum. In the Dirac equation, this is a pseudo-spin, which tells you whether the electron spin is up or down. Here is an actual pseudo-spin, not a spinor, sorry, a pseudo-spinor, which tells you whether the weight of the electron wave function is on the A type of atom or on the B type of atom. Okay? Don't worry, this is the only equation I'm going to show in the entire talk. Okay? The only other thing that I want you to remember is that there happen to be 2 inequivalent of these double Dirac cones in the electronic structure. We call them valleys. And you have the K and the K prime valley. So as a result, electrons in graphene have this 4-fold degeneracy. They can have spin up, spin down, be in the valley K or valley K prime. Just remember number 4. It will appear later. Okay? Now, this is graphene. What happens if you put graphene on top of graphene and you rotate with a twist angle? Okay? So what happens is that a real space Moire pattern forms, okay, where the Moire wavelength, the distance between the soccer balls that you see here in the screen, is proportional to roughly 1 over the twist angle at small twist angles. Okay? Now, this is what happens in real space. Let's look at what happens in momentum space, and therefore what happens to the electronic structure. So this is monolayer graphene. Its electronic structure. This is Dirac cones. This is the Brillouin zone. You have these K and K prime points. If your Fermi energy is here at some finite value, you have these Fermi disks. Okay? And now let's put another layer of graphene on top. If they are perfectly aligned, the reciprocal spaces are also perfectly aligned. Okay? And now, if I rotate the 2 lattices in real space, the reciprocal spaces also rotate. Okay? As a result, the Dirac cones from layer 1 of graphene and from layer 2 of graphene, they get separated in momentum space. Yeah? So twisting leads to layer Dirac cones separated in momentum space. So let's do the following. Let's start from an angle which is already small, so that the separation in momentum space is proportional to the sine of the angle, so therefore the angle for small angles. Okay? And then let's see what happens. So this is the electronic structure that would be, the Dirac cone from layer 1 of graphene, from layer 2 of graphene. They're separated by something proportional to the angle. And this is what would happen if the electrons in one graphene sheet did not know that the other graphene sheet exists. However, when we put these 2 graphene sheets on top of each other, they're only 3 angstroms apart. So the electrons are very much aware that they can go, from one graphene sheet to the other. They can tunnel between the two sheets. Okay? And that tunneling leads to the following. At that point where you have band crossing, you open a gap due to this interlayer tunneling. Okay? This is the same thing as bonding antibonding states in a hydrogen molecule, except that these are bonding antibonding states in a giant graphene molecule. Now, the situation depicted here is for when this interlayer tunneling is small compared to the energy of that crossing point. But as you decrease the twist angle, these two points get closer and closer and closer, and that gap, that band, the lower band, gets pushed down to lower and lower and lower energy until you reach a value for which the interlayer tunneling is of the same order as that energy point there. Then we say that a flat band condition has been realized, and the angle for which that occurs is known as the magic angle, which happens to be 1.1 degrees for graphene on top of graphene. Okay? So this term magic angle was coined by Bistritzer and McDonald. Okay? There was some earlier theoretical and experimental work that already predicted that the single particle physics of the system would have that flat band condition. Okay? Now, this was a schematic. Okay? Let me show you an actual calculation. This is an actual calculation of the energy versus momentum. Okay? These are the flat bands. As you can see, they are not perfectly flat. They have a little bit of dispersion, but this dispersion is orders of magnitude flatter than the original graphene dispersion, this Dirac cone. Okay? Now, flat in momentum space, if we want to look now at where are the electrons that sit in those flat bands in real space, you have to do a Fourier transform. Flat in momentum space means highly peaked in real space. So if you calculate, where are the electrons in these flat bands, they happen to be, the electrons like to sit in certain regions where locally all of the carbon atoms are on top of each other, okay? And those regions are separated by regions called of AB or BA stacking, where the electrons, where the atoms, due to the small twist angle, get out of registry and are shifted with respect to each other. So magic angle twisted bilayer graphene, okay? Schematically, it looks like this. There are these regions of AA stacking where the electrons like to sit. And these are separated by these regions of AB and BA stacking where the electrons do not like to be. In a slightly more realistic schematic, this is what magic angle twisted bilayer graphene looks like. You have these regions where the yellow shading is. Those are the AA regions where the electrons like to sit. Those regions are separated by about 13 nanometers. Okay? So this is going to form the equivalent of a triangular Fermi-Hubbard lattice for my cold atoms. Okay? Now, I put triangular in quotes because in reality this is a honeycomb because these AB and BA regions are not equivalent. And I put in quotes Fermi-Hubbard lattice because this object has interesting topological properties which prevent you a direct mapping to a regular standard Fermi-Hubbard lattice in cold atoms, for those of you that are experts on that. So then how do we do this thing, okay? Like how do a lot of times people ask me, how can you create that structure? It's actually surprisingly simple, I mean, of course, if you ask my grad students, they might disagree, but, let me show you. So we start with a glass slide with a polymer stack, with something sticky. Yeah? Then we bring a substrate which has a material called hexagonal boron nitride. That's a very flat, atomically smooth dielectric. And we just pick it up. Because it's sticky, we just pick it up. Then we bring another substrate which has a monolayer graphene sheet, a one-atom thick graphene sheet in there. Okay? There's something that thousands of groups around the world can do. It's no problem at all. And what we do is we position our hexagonal boron nitride sort of halfway on top of this graphene sheet. We now tear half of the graphene sheet, okay? But of course, both halves come from the same original graphene sheet. So from the top, this looks like that. We have the substrate, we have the glass slide with the polymer, we have the hexagonal boron nitride, and half of the graphene there, and the other half here. But they are aligned crystallographically with respect to each other. Okay? Now, we can rotate the substrate or the slide by any angle that we want, in particular 1.1 degrees, why not? And then we shift it and then we stack it on top. In this process, we pick up the second layer, and then we continue doing our nanofabrication process. And amazingly, this thing produces a long-range ordered pattern of these two graphene sheets at that angle, okay, which creates a periodic Moire pattern. So once you've done this, the rest of the fabrication process is very standard. Many groups around the world can do that. Okay, you have this twisted bilayer graphene at any angle that you want. You connect it to source and drain electrodes. We have dielectrics on the bottom and the top. And we have, these are just for encapsulation to protect the magic angle graphene. And then it's important that we have a nearby metallic electrode. The metallic electrode and the magic angle graphene form a parallel plate capacitor. So by applying a voltage, gate voltage to this in a field effect transistor geometry, we can vary the charge density in the magic angle graphene. Okay? And that's something that we can do electrically. So before I show you data about magic angle graphene, let me remind you what conduction through regular graphene looks like. Yeah? So if you measure the conductivity versus charge density for regular graphene, just monolayer, just one layer, okay? If you have your Fermi energy deep in the valence band, you have lots of holes, so it conducts very well. If your Fermi energy is deep into the conduction band, you have lots of electrons, so it conducts very well too. And if your Fermi energy is at the charge neutrality or Dirac point, you have very few charge carriers, so you conduct poorly. So the conductivity of graphene versus charge density has this V shape, okay, which has been seen and measured by thousands of groups around the world for many years. So let me show you now what the conductivity for magic angle graphene looks like. Huh? So this is the conductivity versus charge density for magic angle graphene, for a magic angle graphene device. As you can see, near charge neutrality, there is still this V shape. But then we have this down and ups and downs, and a lot of structure, okay? So let me guide you through it. Remember that these are the flat bands, okay? So from charge neutrality, from 0, I can add electrons to this band until I get to the very top, or I can remove electrons from this band until I get here to the bottom, okay? In order to do that, to have the chemical potential in this region, okay, to empty this band, I have to take away 4 electrons per Moire unit cell, or add 4 holes per Moire unit cell to my electronic structure. Remember number 4? I told you it will appear again. Here it appears again, okay? When you put your chemical potential here, your chemical potential is in the middle of a band gap, of a single particle band gap. Therefore, you cannot conduct electricity. So you see the conductance, which is 0. We can add from charge neutrality 4 electrons per Moire unit cell. And then we have our chemical potential here, also in the middle of a band gap. And therefore, we also have a band insulator, 0 conductance, okay? These are single particle insulator states. Insulator states that we can understand with simple quantum mechanics. The interesting thing that happens is if I add 2 holes per Moire unit cell, my chemical potential is in the middle of a band. I have plenty of electronic states there. This should be a very good metal. However, my conductivity, my conductance is 0. Yeah? This is something very unusual that it doesn't happen in single particle physics. And this insulator state is a correlated insulator state. It's an insulating state due to interactions between our electrons. The same thing happens if I put 2 electrons per Moire unit cell. The conductance also becomes 0, okay? And that is, again, despite the fact that in single particle physics, simple quantum mechanics should tell us this is a good metal. It's not. It's an insulator. Okay? This behavior only happens when the twist angle between the 2 graphene sheets is in a narrow angular range around 1.1 degrees. Okay? If you put 0.8 degrees or 1.3 degrees, none of this happens. Okay? The system is a very good metal at 2 electrons or 2 holes per Moire unit cell. Now, that was the first thing that we discovered. Then an even bigger surprise happened, okay? So what happened is that if you add a few electrons or a few holes with respect to this insulating state, magic angle graphene became a superconductor. You measure the resistivity of the system as a function of temperature, and it goes down and then exhibits a precipitous drop to 0, okay? Not only that, in a phase diagram of temperature versus charge density, we can see that this superconductivity is electrically tunable. Let me show you here a zoom in, okay? So magic angle twisted bilayer graphene is an electrically tunable superconductor, and there are very few of those. There are not so many, okay? And in particular, when my students show me these data, okay, there is this correlated insulated state, and then we add some holes. This is the state for 2 holes per Moire unit cell. We add extra holes, we have a superconducting dome. We add electrons, and we have another superconducting dome. When my students show me this data, it reminded me immediately of the hundreds of times that I have seen data such as this, okay? This is a phase diagram of the high-temperature cuprate superconductors, where, let me actually flip this axis so that, okay, now it's correct. Okay, that's in the same axis as this. At 0 doping concentration, which means 1 electron per copper atom, as I said before, you have a mode insulated state. You add holes, and you have a big superconducting dome. You add electrons, and you have another superconducting dome. Now, here we have a 2 holes per Moire unit cell, a correlated insulated state. You add holes, and you have a superconducting dome. You add electrons, and you have another superconducting dome. Now, there are some similarities and also many differences between these 2 pictures. But one of the biggest differences is that this is a theoretical phase diagram. In order to populate this with data points, I have to grow hundreds and hundreds of crystals. Each growth is different, with a different chemistry, with a different type of material, and with a different disorder, okay? This is all done in a single device, in a single cooldown, in a single disorder realization, and I can go from here to here in 10 seconds and measure this entire thing, okay? So that's something, you know, that obviously is an advantage of this type of systems, the fact that we can control the doping level electronically. Now, so, you know, we posted, you know, as Eric mentioned, you know, we announced these results at the APS March meeting in 2018. And then, you know, the theory tsunami came, you know. So this is just a few of the papers that appeared within a few weeks of us posting our results on the archive, you know. There were all kinds of papers, you know. The first one was by Zenke Xu and Leon Valens, saying this was a D plus ID chiral topological superconductor. The people are interested in what is the origin of these correlated insulated states and the superconductivity, or the parameter. But, you know, people in this community, very creative, they proposed all kinds of order parameters with all letters of the alphabet, you know, S plus P, S plus P plus D. Now F is a very popular one, you know. In fact, I always joke that in the graphene community where I used to work, the angular cone of disagreement between theories was about 20 degrees, you know. But in this community, it's 360, you know. In fact, it's 4 pi in all directions, you know. So it's really, for me, it's quite amazing, you know, how much more complex is the theory in this field. Now, you know, besides the theory tsunami, you know, so this is just a few of the papers. By now, that list actually has several thousand papers. The thing that also was interesting is that it raised a lot of, you know, attention in the popular press, you know. So people will, I wish I knew how to design these kind of cool pictures, you know. And it attracted also, you know, and it made it into some popular magazines. Now, let me tell you, you know, more seriously what were the experimental developments, or, you know, give you some examples of some experimental developments that happened since the paper was officially published in April 2018. So the first thing that happened is that we have reproduced our own results, you know. Believe it or not, that doesn't always happen, so it's good when it happens, okay? We were able to do this again, and we've done it many times. And in fact, by now, we are starting to produce a map of the critical temperature as a function of twist angle. That's a new knob, a new parameter in condensed matter physics, okay, for these devices. This is actually already a bit old. We have many more data now. The second thing that happened is that, you know, and that's much better than you reproducing your results, is when other people reproduce your results. Only then it becomes real science, okay? So many groups have independently reproduced our results and extended them in very interesting directions. So the first 2 papers to reproduce our results, you know, was the first one is a collaboration between Corey Dean at Columbia University and Andrea Young at UCSB. Not only they reproduced our results, they also extended them in a very interesting experiment under pressure conditions, and they were able to tune the superconductivity in this system. So that was fantastic. And then the group of Dimitri Efetov at ICFO Spain, they were able to see additional superconducting domes in a particular device that they have. By now, robust superconductivity has been reproduced and extended by many groups, about over a dozen groups, and many more groups join, and I'm sure Eric's group here will soon start producing devices too. And the next thing that happened is that we have measured plenty of other phenomenology which is characteristic of traditional quantum materials. For example, strange metal behavior and nematicity. Let me just mention this strange metal. And, in this phase diagram of the cuprate superconductors, this biggest part, this biggest wedge is this strange metal thing. Okay? So the strange metal phase is characterized by strange behavior, hence the name. Okay? Basically, it means we don't know what's going on. But in particular, that strange behavior of many properties, one of the most characteristics is that the resistivity is linear in temperature at low temperatures when it should be quadratic. Okay? Now, as soon as you get out of the superconducting state, in the cuprates, the resistivity versus temperature is linear. And here, these are data for magic angle graphene. As soon as you get out of the superconducting state, the resistivity starts being linear in temperature. Okay? In fact, we can take a sample where the critical temperature, again, because we can tune this, the critical temperature is very small, and then it starts to be right away linear in temperature. More recent data from the group of Dmitry Efetov have shown that this linear in temperature behavior can go down to 40 millikelvin. It's one of the systems, it's one of the strangest metals. One of the metals where the resistivity goes linear down to the lowest temperature seen of any material. Yeah? Now, there is also, we have discovered several other correlated systems using this twistronix platform. For example, ABC trilayer graphene aligned to HBN, or magic angle twisted bilayer graphene. Okay, so let me tell you what that thing is. You can have 2 layers of graphene with 0 angle between them, the way they usually are in graphite. You can have another 2 like this, and you can now put them on top of each other and twist them pairwise. Okay, so we call that twisted bye-bye, and that happens to be also a strongly correlated electronic system, which is much more tunable electronically. Okay, so for example, this is quite complex. All I want you to see is that red means insulating states, and in this map of gate voltage, top and back gate voltage, you see we can tune such that that correlated insulated state appears only in certain regions, okay? And that's because we can tune all the parameters of our system electronically. There have been lots of scanning probe microscopy results. People are starting to look microscopically at what's really going on with these Moire patterns, okay? A few years ago, a couple of years ago, there was this very interesting week in Nature where they reported scanning tunneling microscopy, the first scanning tunneling microscopy experiments on magic angle graphene, and there were these 3 papers in Nature appearing in the same week, okay, by the groups of Abhay Pasupathy, Eva Andrei, and Ali Yazdani. There was a paper in Nature Physics by, let me give it proper credit, by Stefan Nachberg, okay, all reporting very similar results. In particular, what they were able to show is that, in STM, the nice thing that you can do is that you can tune the chemical potential in your system, but you can also spectroscopy at a higher energy. And what they were able to see is that, this is again complex. All I want you to pay attention is to the fact that these 2 lines, which also continue here, are very close together, and they broaden when your chemical potential is in those flat bands. Okay? Which means if you are occupying those flat bands, lots is going on. Your electrons are strongly interacting, and they're increasing the bandwidth of your system. Okay? And that was a direct demonstration of the strongly correlated nature of these objects. Perhaps the most interesting thing that happened after, after the original discovery was the fact that people measured ferromagnetism, anomalous Hall, and quantum anomalous Hall physics in the systems, which brought the role of topology front and center in the systems. Okay, so in fact, one of my biggest satisfactions, is that I now talk to many people that I used to not to talk to because I didn't have too much to share. I didn't have much in common with them. But Moire quantum matter, this field has meant the merging of several modern condensed matter communities. On one hand, is the people that did 2D van der Waals heterostructures and materials like myself, I was doing. Then you have the people that did strongly correlated materials like the cuprates, the pnictides, the heavy fermions. And then you have the people that did topological condensed matter physics, quantum and fractional quantum Hall effect, topological insulators, topological semimetals. All of these three communities come together in this field of Moire quantum matter. And now I participate in conferences and I talk to many people that I used to not interact with, and that's one of my biggest satisfactions. In 2019, my theory colleagues, and ourselves, we just provided a little bit of inspiration. It was really the work of my colleague, Senthil Todadri. We predicted for a whole bunch of Moire heterostructures that these would have interesting topological properties and they would have nearly flat Chern bands in these Moire superlattices. And there was a lot of other related theoretical work. And just within a few months, the group of David Goldhaber-Gordon measured these very large anomalous Hall effects. So they demonstrated a new type of ferromagnetism, orbital ferromagnetism in this system. This was in structures. It was in magic angle graphene, where one of the graphene sheets was aligned to the hexagon laburnite, partially aligned to it. That breaks the symmetry in the system that enables this ferromagnetism. And then a few months later, the group of Andrea Young at the University of California, Santa Barbara, they actually reported the quantized anomalous Hall effect, actual quantization of the Hall conductance, so quantum Hall effect at zero magnetic field in these structures, okay? In a structure which has no magnetic impurities of any type or anything like that. So that was very remarkable. The group of Feng Wang, shortly after, reported similar quantization, quantum anomalous Hall effect in an ABC graphene aligned to HBN, which is a different Moire heterostructure. And since then, there have been a number of Moire systems where these topological properties have been investigated. Now, we're busy now with the next generation of Moire quantum matter. I call this Moire Magic 3.0, okay? So last year, the group of Philip Kim and my group, back to back in the same week, we published in Nature and Science the discovery of a new robust Moire superconductor. It's magic angle twisted tri-layer graphene. So this is, one layer of graphene, another one rotated back, so 3 layers in total. It is an even more interesting superconductor than the bilayer itself, much more tunable and more strongly coupled. In particular, one of the things which is interesting with both the bilayer and the tri-layer case is the following. So when you discover a new superconductor, you can wonder, okay, how strong is the superconductor? And one way of characterizing that is by saying, what is the value of the critical temperature, the absolute value of the critical temperature? That's okay. It's important for applications, but it's not the one that gives you the more physics information about how strong the superconductivity is. What typically we do is we create a plot where we have, it's a log-log plot of the critical temperature of the superconductor versus the Fermi temperature or density of electrons in the system, okay? In this plot, I'm going to put a few lines here. In this plot, conventional superconductors, such as aluminum, they tend to be near this corner, okay? So for example, aluminum has a TC of about 1 Kelvin and a Fermi temperature of over 100,000 Kelvin. Given the gigantic density of electrons that aluminum has, it superconducts relatively modestly, okay? As you go towards this band here, this purple band here, you have, as you go diagonally in that direction, you have more and more exotic type of superconductors. In fact, in that purple band, we have all of the unconventional superconductors that we know. We have the cuprates are here, the heavy fermions, the organics, the heavy fermions, the pnictides, the organics, they're all here. Okay? Now, if you look at magic angle twisted bilayer graphene and magic angle twisted tri-layer graphene especially, these are among the strongest, if not the strongest, superconductors that we know. They have a minute density of electrons, just a few electrons, and they superconduct very strongly. They have relatively high TC. If the high temperature couplet superconductors had the same coupling strength as magic angle graphene, they would be well above room temperature superconductors. Okay? So one of the mysteries in the field is how come that magic angle graphene and the tri-layer graphene, how come that with so few electrons, they superconduct so strongly? What is the key physics, the key ingredient that allows that to happen? And can we recreate that key physics in other materials at higher densities? And higher densities will mean much higher critical temperatures, okay? Possibly room temperature. So I should mention that some other materials recently have also reached these limits. Now, magic angle twisted tri-layer graphene not only is a very strong coupled superconductor, it seems also to be a superconductor which is not described by spin singlet Cooper pairs as most superconductors are. So, because this is a two-dimensional superconductor, you can apply an in-plane parallel magnetic field, okay? And that means that you can observe mostly the effect of Zeeman splitting on the superconductivity. Okay? Usually, if you apply a perpendicular magnetic field to this 2D plane, you induce vortices and you create all kinds of physics, which just makes the problem more complicated. But if you apply an in-plane magnetic field, you can look just at Zeeman, or that's what people thought. Now, in a conventional superconductor, Cooper pairs are entangled states of spin up and spin down. Yeah? Now, in a conventional superconductor, you have the binding energy, the superconducting gap in VCS theory, it's given by this formula, which is proportional to Tc, to the critical temperature. When you apply a Zeeman field, because you split spin up and spin down, by the time your Zeeman splitting is equal to your superconducting gap, you have destroyed superconductivity. Yeah? That leads to this Pauli limit, is known, or paramagnetic limit, or Chandrasekhar-Clarkson limit, which tells you that your critical field should be, at most, about 1.86 times Tesla per Kelvin times Tc. So for 1 Kelvin Tc, 1.86 Tesla. Okay? And that happens for all conventional superconductors. Now, what we have discovered in magic angle theory is Trilagiography. Okay? I'm just going to flash it, not give any details. But this system violates this Pauli limit by a huge factor. Okay? If you measure the resistivity, this is the region of superconductivity. Resistivity versus temperature and parallel magnetic field. Superconductivity should disappear at this value, but you can see it's much, stays superconducting at much higher values. Okay? That's very strange. And not only that, you can kill superconductivity. You can keep increasing the magnetic field, and then it reappears. That's even stranger. We know a few examples of this. Of this, there are literally 3 or 4 examples in the world of materials that do that. Okay? And they are all non-spin singlet superconductors. Okay? Now, I told you that we are busy with Moire Magic 3.0, but actually we continue. So now we have Moire Magic 4.0 and 5.0. Okay? As of a few months, a couple of groups and ourselves. Okay? As you can see in this field, the competition is huge. You post a paper, and then immediately 3 papers appear in the archive the same day or so. What we have discovered recently is that the magic angle multi-layer graphene is a family of robust Moire superconductors. Theorists have calculated what are the magic angles for any number of layers of graphene, and we have very patient graduate students who were stuck in these things with angles, and putting more and more layers on top of each other. And what we have discovered is that these are all superconducting. So this is a robust family of superconductors. There's now a new family of superconducting systems called the Moire superconductors. And we have done it for 2, 3, 4, 5. Presumably, it's for any number of layers. You can realize this. Now, in the last, few minutes of my talk, I want to move beyond graphene to show you that, Moire magic also happens, without carbon. And I'm going to tell you about Moire ferroelectricity in bilayer boron nitride. So, when we started to work on this, Moire structures, we saw correlated insulators, superconductivity, topological phases, magnetism, pneumaticity. At some point, there was this question of, wait a moment, there is this other emblematic, phase of condensed matter physics, ferroelectricity, which is not there. Is it possible to find it? Okay, and then we spent, maybe 6 months or a year working on this, and again, 3 papers appeared in the same week. Again, you post it, and other people work. We all 3 papers, posted the discovery of, various names: interfacial, stacking engineer, or charge polarizer interference. So, this is all the discovery of Moire. Or stacking engineering ferroelectricity. And this is something which, in general, in condensed matter physics, orders don't like to exist in 2 dimensions. Okay? There is a famous theorem that forbids that you can have ordered states in 2 dimensions, but as most theorems, they don't really work, and we still have order in 2 dimensions. But it's rare. If you take a superconductor and you make it 2D, typically it weakens or disappears. If you take a ferromagnet and you make it in 2D, typically disappears because of fluctuations Huh? So with ferroelectricity, it's similar. There are only a few, I think these are all of them, two-dimensional ferroelectric materials. Yeah? And these ferroelectric materials essentially all come from exfoliating a bulk material which is ferroelectric. Yeah? So perhaps it's not too surprising if somehow you find a loophole in this theorem, the 2D version is also ferroelectric. What I'm going to tell you about today, now, is different. In the spirit of graphene, which is not superconductor, I can put it on top of graphene and I get a superconductor. I'm going to take a material which is not a ferroelectric, I'm going to put it on top of itself, and it's going to become a ferroelectric. Okay? So that's sort of the magic of the type of things that we can do with this non-equilibrium assembly of 2D materials. So the material I'm going to talk about is hexagonal boronitride. I've already mentioned this material as a nice dielectric for graphene devices. Now we're actually going to make use of it. Yeah? So bulk bilayer boronitride, or just bulk hexagonal boronitride, has also a honeycomb structure, okay, where now the A and B sublattices of graphene are actually different atoms, boron and nitrogen, okay? So they form a honeycomb atom, a honeycomb layer. Now, if you have two layers of boron nitride which have been extracted from a bulk crystal of boron nitride, okay, it turns out that the second layer is rotated by 180 degrees on top of the first layer. That's the natural growth of this material, okay? And this thing is centrosymmetric. It's not a polar material. It's not a ferroelectric material. It doesn't have a permanent electric dipole moment. Okay? Now, remember that I can do whatever I want with the second layer because I can choose whichever angle I want to put it on top of the first, right? So I can do the following trick. I can take a monolayer of boron nitride. Let me put lines to guide your eyes to the nitrogen and boron atoms. I can tear it and put it on top of itself, but instead of 180 degrees, like nature would like to do it, I just align it 0 degrees, exactly on top of itself. Now, that's very uncomfortable. The boron atom doesn't like to be on top of a boron atom, and the nitrogen on top of a nitrogen atom. So what happens is that the system shifts laterally, and it goes into one of two options, an AB stacking configuration or a BA stacking configuration. And it turns out that these two different configurations have opposite electric dipole moments. So if you can switch somehow magically between these two, you have a switchable ferroelectric. You can perhaps a memory element, for example. So this is exactly what we did. We created these parallel bilayer boron nitride layers. And in order to investigate its ferroelectricity, we deposited a graphene sheet on top. And then we deposit more dielectric and a bottom and top gate so that we could apply an electric field. What we did is we created a ferroelectric field effect transistor. A transistor where the conductance, the resistivity of the transistor, depends on the polarization state of the ferroelectric. So when you measure the resistance versus electric field for such a device, okay, remember that I told you the conductance has V shape for graphene. Resistance, which is 1 over conductance, looks like a peak. Okay, the opposite 1 over a V shape, which is a peak mountain. So if you sweep in one direction, the electric field, you have this maximum and then like this. If you reverse and sweep in the opposite direction, you have the same thing, but shifted. You have hysteresis. Okay? And that hysteresis is the signature of this ferroelectric behavior. So you can do this in a continuum manner as a function of, bottom gate and top gate. You can see that you switch, and this resistive peak abruptly changes when you go from BA to AB type of stacking. If you then reverse, it switches at a different point. That is the hysteresis. Every now and then we're lucky and we catch a domain wall sweeping through our contact, so we see a bistable, the two resistive states. Now, this is so far 0 degrees. If I twist them by a small angle, I can realize actual Moire ferroelectricity, okay? Where now, when I put a twist angle, I'm going to have these ABBA domains similar to magic angle graphene, except that these now are very different. They have opposite electric dipole moments, those domains. And if I apply an electric field in one direction, I'm going to increase one type and shrink the other. And if I apply it in the opposite direction, I'm going to do the opposite, okay? So we fabricated, small twist angle, twisted bilayer boronite at 0.6 degrees in this case, similar graphene ferroelectric field effect transistor geometry. And now we can see that there is a gradual change from one resistive state to the other, okay? As opposed to a sharp, abrupt state, because now we have this Moire ferroelectricity, which is shrinking and expanding electrically tunably, okay? Now, do we actually have direct visualization of this thing, okay, of these AB and BA domains? It turns out there is a technique that allows you to see this. It's called piezoelectric force microscopy. And when you image one of these devices, okay, twisted, you can see this. This is the amplitude, this is the phase, this is telling you the opposite electric field, of these ABBA domains. You can put this on top of this, and you can see that it matches exactly. Okay? Not only that, this thing works at room temperature. It's about the only thing in my life I've done that works at room temperature. Usually I go, 4 Kelvin is high temperature for me typically, but this thing actually works at room temperature. So you can actually make a memory element out of this, and you can repeat it as many times as you want, etc. Even better, we've done this thing with hexagonal boron nitride, but if you think about it, the only thing that we needed was to have this bipartite lattice. So we can, this crystal symmetry engineering that we did in boron nitride, we can try to see if we can recreate it in any other bipartite lattice. So in particular, we did this with the transition metal dichalcogenides, which are also single unit cell semiconductors. They look from the top similar. You see this honeycomb lattice with alternating metal and chalcogen atoms. And we can parallel stack them on top of each other. This leads to different opposite electric dipole moments. And we have made twisted structures of all of these materials, WSE2, MOS2, WS2, MOSE2. So all of them become ferroelectrics, okay? So in a process of about a year, we have doubled the number of two-dimensional ferroelectric materials which are known, okay? And not only that, with the same trick, you can engineer ferroelectricity into any material as long as it has this bipartite lattice, which could possibly have simultaneously other orders. You can make superconductor ferroelectrics, ferromagnetic ferroelectrics. You can do so many other things, okay? And this is something that, is one of the few things that I have my engineering colleagues at MIT calling me on the phone to talk about this, So usually they don't call me. So now, let me just in the last couple of minutes tell you a little bit about what's going on in neighboring or some of the outlook. So I showed you again, all of these things that we have discovered in many systems, all of these phases of matter. We have just used very simple elements to discover all of this. Graphene, hexagonal boron nitride, and some transition metal dichalcogenides for some of the things that I've shown you, okay? But we have hundreds and hundreds of two-dimensional materials, some of which are very exotic by themselves in monolayer form. The high-density cuprates, or we have plenty of superconductors which are monolayer in form. We have ferroelectrics, which are monolayer in form. We have magnets and quantum spin liquids, which are monolayer in form. So imagine, if we now start stacking them on top of each other, twisting them, etc. Okay? So we have infinite possibilities to realize more exotic types of Moire quantum matter. Experimentally, it's a bit hard to do, but theoretically, it's very easy. And theorists are now churning out hundreds and hundreds of papers about all these possibilities. Okay? So I'm showing here just two of them. So you have the group of Marcel France has predicted that if you stacked two monolayer cuprate superconductors on top of each other above a certain angle, you will have a high-temperature topological superconductor. Okay? A very different type of superconductivity that is present in the cuprates. If you take two-dimensional magnets and you stack them on top of each other, you can create Moire magnets, which have all different kinds of Moire skirmions and spin textures, etc., which you can also control. Okay? So there are plenty of things. These are just two examples. In fact, all of the things I've mentioned to you today are related to twist electronics. But people in other communities have realized about this trick, and it turns out it can be extended to many, many other types of physics. Okay? So for example, the cold atoms people are starting to make Moire and twisted cold atom lattices. Okay? So there are papers already predicting all kinds of behavior in these lattices. If you take phonons, even classical vibrating plates, you can do the same thing, and you can make magic angle acoustic, they call it magic angle, acoustic twisted bilayer graphene, where you can slow down the speed of photons, to very slow speeds, and you can do all kinds of things. You can imagine how that can be important for thermal transport and all kinds of things. The people in photonics are going crazy about this thing, because you can also do all of these tricks with photonic lattices and slow light to very slow speeds, and do all kinds of things. So all of this physics, and this is much more tunable, in fact, in photonic systems, because you can tune the coupling between the two systems which you're twisting arbitrarily. They have a lot of design flexibility. So people are doing all of these things, and the list continues. People are doing Moire chemistry and electrochemistry and Moire catalysis, because these systems have high density of states, and you name it, okay? There's a lot of things that are going on, which I didn't have time to tell you about. So with this, I want to end, with the most important slide. All of this is largely the work of, my fantastic group of graduate students. For what I presented today in particular, Yuan Zhao, Daniel Rodan, and Jane Park, did the key things related to graphene, and Kenji Yasuda as a postdoc, and Shirui Wan on the ferroelectricity. I have plenty of collaborators at various institutions. We're starting to go back to some events like this, I hope we will fully, in the next months, be back to that. And I want to also thank all my funding and sponsors, and thank you all for your attention. And I'm happy to take any questions.
So please raise your hand if you have a question, and someone with a microphone will come find you. Over here, Lou has a question.
Oh, the microphone?
Oh, we need, here they are.
Thank you. Beautiful talk.
Thank you.
Each time I listen to your talk, I learn something new. And
Thanks.
here I like to learn, actually, I wonder, one particular one was your very first paper, resolving two correlated insulating states by gating. Looking at your diagram, right? I would imagine you would just cross that two electron once as your gate. Why you cross it twice?
You cross it twice because you cross the two holes per Moire unit cell,
Right.
and then you cross the two electron per Moire unit cell. So
I see. So
that's
you
why
move
you cross
upwards and
twice
backwards. I see.
Even number of, even integer number of electrons per Moire
Right.
unit cell.
Right, very interesting. So now what's the standing of the nature of the correlated states? Is that still a mod thing, or it's more, there's still debates about what's going on?
No. So initially, back then, the fact that it occurred at an integer filling factor was, the closest thing that we found was mod-like type of physics. What is becoming now clear is that there is a phase transition taking place actually at each integer number of electrons per Moire unit cell to a broken symmetry state, and that broken symmetry state is what becomes an insulator, at each of those integers. So it's still due to strong interactions, but I don't think you can call it a mod state because you're actually breaking the symmetry.
I see, thanks a lot.
I have a question. Is there a path out of gut feeling to room temperature superconductivity?
So, people always ask me that question, which is, of course, a very tricky one. Let me just go back to that slide with the Uemura plot. Let me wait. Takes a while to connect. Yeah. So in this plot, the superconductors which are strongest, in some theories, the reason why there are these dashed lines is because in some theories, okay, in some models, this is a limiting factor for how strong it can be. It turns out to be not a strict limitation, and it depends on the type of system that you have, but it serves as a guide. As you can see, the vast majority of superconductors are below that line, okay? So that means that, let's imagine you get a very strong superconductor, like magic angle twisted Trilagiography. If you were able to maintain that coupling strength, you would be riding as you increase the Fermi temperature along this line, okay? So in order to make a room temperature superconductor, something that will be up there, the line will be 300, you would need a superconductor which is as strong as magic angle graphene at a density, at a Fermi temperature of 10,000 Kelvin, which is smaller than most metals, okay? But you need a much stronger concentration of charge. With these Moire systems, okay, we don't know yet how to do that. They're very diluted, okay? These Moire wavelengths are very large, of the order of 10 nanometers. That's why you get a super small Fermi temperature, okay? We would have to, an idea that some people told me is like, oh, maybe if we can modify the magic angle condition, for example, with pressure, such that you can do this at larger angles. Larger angles means smaller Moire wavelength, so you're riding up in density. In practice, that will take you, even for the largest pressures you can apply in an experiment on Earth, it will take you maybe here to 10 Kelvin or something like that. With these Moire systems, with the simple scheme that we have, I don't think we will get to something like room temperature. What a lot of people hope is we do not understand why these systems are the strongest superconductors that exist. But if we get to understand that key ingredient, like, oh, we need to have this particular electronic structure, this particular combination of elements, whatever, perhaps we can translate that into an engineering design for a real material with real atomic scale densities that will result in room temperature superconductivity. And that's something that we could hope for, but it's not obvious at all that will happen.
Hi, I'm not a physicist, so I'm going to ask a really stupid question.
No, please.
With the boron nitride, was it? It's a two-layer thing, so there's a little gap between the two layers.
Mm-hmm.
But what happens if you try out graphene with a gap of a similar size, so the size is similar to the distance within the
So do you mean, so
if you stack
whether it's graphene on top of graphene or boron nitride on top of boron nitride, there is also an interlayer spacing, okay? That interlayer spacing is the gap that results from the electronic repulsions between the orbitals of the two elements that the two sheets that you're putting on top of each other. So there is always a spacing, which is actually the same spacing that you find in the natural crystal, okay? So when you make a crystal of graphite, there is a distance between the planes of graphite, which is 3 angstroms. Is the same thing in the structures that I'm creating. It's 3 angstroms, okay? It's not an artificial extra spacing that we have.
So if you did make an artificial extra spacing, it would just make it kind of go out of focus, or it would have a different effect, or what would happen?
Very good. So remember that I told you when I explained how this magic angle comes about, this magic angle condition, it has to do with the tunneling of the electrons between the 2 graphene sheets that I put on top of each other. That tunneling between these 2 electrons is very sensitive, exponentially sensitive to that distance. That's why in experiments where they applied pressure, they put those 2 planes a little bit closer together, and they could change the angle, the magic angle condition. If you were able to pull them apart, which is actually quite tricky, but let's imagine for a moment you were able to continuously pull them apart, that would change the magic angle condition because you would be tunneling differently, okay? No one has been able to pull them apart. What you can do is you can insert another layer in between that will artificially separate these 2 graphene sheets apart. For example, I can put a monolayer of HBN, hexagonal boron nitride, which is an insulator in between, and then these 2 graphene sheets are further apart, okay? So no one has found the magic angle condition for that, but it's something that you could do. And for transition metal like chalcogenides, for some other elements, people have done that thing and found very interesting physics in trying to pull them apart a little bit. Yeah? So it's actually very, very rich physics that you can do with something analogous to what you propose. Yeah. Good idea.
Very nice talk. So I have a question about the reentrant effect you mentioned about applying magnetic field. So do we know the pairing symmetry or whether it's spin singlet state or triplet state for the reentrant superconducting base?
So what my theory colleagues tell me is that at low magnetic field, there is again some theorem that prohibits purely spin triplet type of superconductivity. Okay? So it is most likely that the order parameter has a combination, a linear combination of spin singlet and spin triplet. It's called spin valley locked. Now, at high fields, that theorem doesn't apply anymore, and it is possible that the reentrant phase is actually a purely spin triplet type of superconductivity. But we don't know yet. We have to still investigate it.
Thank you.
As I said earlier, I never trust too much the theorems, so they end up not applying, so.
Other questions? Okay. Well, if not, let's thank Pablo again for just a fantastic talk. Thank you.
Thank you very much.